Throughout most of the course, we've been talking about matrices as representing some system of equations, right? Well, we can reformulate this in the language of linear transformations. So I'll just start with the definition here. We can say that T of X, which we know if it's linear, there exists some matrix A, such that T of X is A times X, right? Well, T of X equals B. This is a linear system of equations. If we find some X sub P such that it satisfies this solution, or satisfies this system rather, so we have that T of X sub P equals B, right? Then we say X sub P is a particular solution to the system, okay? So if you find just any solution to this system, X sub P, then we say that this is a particular solution. Well, what we're going to do is we're going to come up with general solutions. So here's a theorem. So these are general solutions. Let's say X sub P is a particular solution to T of X equals B, okay? If Y is any other solution, then there exists, let's say X naught in the kernel of this transformation T, such that the solution Y is expressed as the particular solution plus this X naught of T here, where X naught is a solution to the corresponding homogeneous system. And remember, what does it mean for a system to be homogeneous? Well, it means it's equal to the zero vector, right? So, i.e., X naught, the vector X naught lives in the kernel, right? We've already stated that, but X naught lives in the kernel and it solves T of X naught equals 0. Or let's just say it solves T of X equals 0, right? And this Y here is this collection of all possible solutions here. This is called the general solution, right? This family of solutions, we just call this the general solution. So first, before we do any examples or anything, let's kind of build up this notion of understanding these homogeneous systems as being the solution space of the kernel. So let's remember a definition here that we'll call the kernel, sometimes we'll call it the null space. So kernel of T is the null space, or the solution space. It's the subspace of solutions of the homogeneous system. So it's the solution space of T of X equals 0. So let's find an example of computing the null space, right? Because really the null space or the solution space of this homogeneous system is going to be the collection of these elements of the kernel X naught, right? So what we need to do is understand how to compute a solution space to a homogeneous system, or equivalently, how do we compute the null space of a linear transformation? Well, let's look at an example. Let's try to find the kernel of the derivative, we think of the derivative as an operator, right? Normally we just think about the derivative of it in terms of like rules, like the power rule, the chain rule, et cetera, et cetera. But really what the derivative is it's a linear operator that takes a function as an input, it goes through some process and it spits out another function, right? And so the derivative really, in terms of linear transformations, or in this case, linear operators, we think of the derivative as just a function of functions. So if we were to define, let's define some sets very quickly. So if we have C sub 0, let's say F is a map from the real numbers to the real numbers, right? This is a standard function whose graph would live in the XY plane. Well, we can define C0 of F. Let's let this be the set of all continuous functions. We could define C1 of F to be the set of all differentiable functions. And notice that differentiable functions are a subset of continuous functions, right? There exist continuous functions that aren't differentiable. There exist continuous functions whose derivative doesn't exist. For example, the absolute value of x is a continuous function whose derivative does not exist at the origin, right? Of all differentiable functions. And then we could set C2 of F. This could be the set of all twice differentiable functions. And you could define this inductively, right? So where all the way down to like say C sub n of F. So this is a set of all twice differentiable functions for C2. And then for Cn, this would be the set of n times differentiable functions. This chain of inclusion would terminate eventually when you consider C infinity of F. And this would be the set of all smooth functions, or the set of functions whose derivative exists. You can take the derivative of this function as many times as you want. For example, trig functions, right? You can take the derivative of a trig function infinitely many times. The derivative of exponential functions, well, the derivative of e to the x is itself, so you could do that an infinite number of times, right? So this would be, and we just say, for something that's infinitely differentiable, we call it smooth. So this would be the set of smooth functions. Right, so now that we have this kind of language here, what is the derivative as a function or as a linear transformation? Well, the derivative as a function, d dx, what it does is it takes an element of C1 of F, right? F, and it spits out another function. And this function may or may not have a derivative, right? So let's just say the output is C0. So here the derivative is taking a differentiable function as an input and the output is a continuous function. Maybe differentiable again. If so, it belongs to C2, right? Et cetera, et cetera. And so the result of the derivative, well, it's a map f as an input, and then the output is df dx, right? Or f prime. And so let's say we want to find the null space of the derivative, or like what's the kernel of the derivative if you're viewing the derivative as a linear operator. Well, the kernel of d dx as a set, it's going to be those functions, those differentiable functions such that df dx equals 0, right? So the kernel of the derivative is those functions that have a trivial derivative. Well, whose functions have a trivial derivative? Those that are constant, right? If you take the derivative of a constant, you get 0. Take the derivative of anything else with any variable whatsoever, you're going to get something non-trivial for the derivative. So really, the kernel or the null space of the derivative is f in C1 such that f of x equals k for k constant for all x, right? And so this would be the null space of the derivative. It's just going to be constant functions, right? If you'd like to see this a little more informal. This is constant functions. And so constant functions would make up the solution space to this linear system of equations, right? df dx equals 0. This is how we think of the null space, or how we think of the solution space to a homogeneous system of equations. Okay, so what does that mean then, right? That means this collection of constant functions would represent our x naught in the language of the previous theorem that I was talking about here, where we're saying that, if you have a particular solution to a system, then y equals the particular solution plus these solutions or these elements of the solution space or of the null space. The sum of these make up the collection of general solutions here. So let's see an example. Let's say we want to find the null space of the matrix A, where A is the 3x4 matrix given by 1, 2, 4 in the first column, 2, 1, 5 in the second column, 3, 1, 7 in the third column, and 0, 2, 2 in the fourth column. All right. How do you find the null space of a matrix? Well, you set up a homogeneous system of linear equations, i.e., null space of A is those vectors x such that ax equals 0, right? This is exactly the kernel of a linear transformation, which is synonymous with the null space of the matrix representing said linear transformation. So what we would need to do then is we need to set up the system ax equals 0. So we have the matrix A, 1, 2, 4, 2, 1, 5, 3, 1, 7, 0, 2, 2 times x. Well, this is a 3x4. So for matrix multiplication to be defined, the vector has to be a 1x4 vector, right? And so we would have, let's say, x, y, z, w. And then this is equal to the result of this matrix multiplication would be a 3x1 vector. So we want this vector to be 0, 0, 0. So that's exactly right. So now reworded, the null space is this collection of vectors x, y, z, w, such that this system has a solution. How do we find the solution to this system? Well, we create an augmented matrix that represents this system. So that would be the matrix A, 1, 2, 4, 2, 1, 5, 3, 1, 7, 0, 2, 2. And then we augment with the 3x1, 0 vector, right? How do we solve this system? Well, to solve a system of equations, we convert this augmented matrix into its reduced row echelon form, and we're pretty comfortable at doing that by now. So I'll just go ahead and say what I got. We got 1, 0, 0, 0, 1, 0, negative 1/3, 5/3, 0, 4/3, negative 2/3, 0, 0, 0, 0. And you may notice we have 4 variables with 3 equations, and in the reduced row echelon form, we have a row of all zeros. So that means we're going to have 2 free variables, or we're going to have 2 parameters. So let's say z and w without loss of generality. Well, there is no generality here because the first 2 rows of the equation define what's free and what's dependent, right? And so let's let z and w, let's let these be our free variables. Then the solutions to this system are, well, looks like we have, let's be explicit here. Let's be explicit. So we have x minus 1/3 z plus 4/3 w equals 0 for the first row of the matrix. For the second row of the matrix, we have y plus 5/3 z minus 2/3 w equals 0. And then we have, z equals z and w equals w. That's exactly what it means to have free variables. Well, solving for x and y, we get the following solutions. X, y, z, w is the x components are going to be 1/3 Z minus 4/3 W. The Y component is going to be 2/3 W minus 5/3 Z, and then Z is Z and W is W, right? So the null space of the matrix A, right? That's exactly the set of solutions to this system. So the null space of A is then going to be the set of vectors, and it looks like we're going to have Z times 1/3, 2/3, 1, 0 plus W times negative 4/3, no, Z 1/3, excuse me, that should be negative 5/3 for Z, and then for W, we should have negative 4/3 and 2/3, 0, 1, right? So if you'd like to understand the null space as a spanning set, this would be the span, and it's a two-dimensional null space because we have two basis elements here. That's 1/3, negative 5/3, 1, 0, and negative 4/3, 2/3, 0, 1, right? So here's how we would describe the null space of this matrix. And remember, this is also the solution space to the homogeneous system of equations, or the homogeneous system of linear equations generated by setting the matrix A times vector X equal to 0 here. And so now we know that the general solution is a particular solution plus basically all of this family of solutions, right? This is exactly your family of vectors X naught here, right? When we were looking in the language of the theorem we stated earlier, this is exactly when you find the vectors that are the elements of the null space, that's exactly these X naught here, right? There are elements of the kernel. And so to find the general solution for a given linear system, what you have to do is you have to find a particular solution, and then you have to find the null space. You have to find all elements of the null space. And then all sums of these, this makes up your family that's called the general solution to a linear system of equations. So let's look at an example that piggybacks off of the one we've just done. So example here, let's say we want to find the general solution to the following system of equations. And we'll go ahead and just write this system in terms of, or represent it as a product of matrices. So 1, 2, 4, 2, 1, 5, 3, 1, 7, 0, 2, 2. Notice it's the same matrix A, and X, Y, Z, W, same vector X. But now instead of it being equal to zeros, instead of this being a homogeneous system, let's set this equal to 9, 7, 25. And we want to find the general solution to this system. Well, the general solution is given by those vectors Y such that, oh, I'm getting ahead of myself here. We're also given, this example's too nice. We're given that X, Y, Z, W equals 1, 1, 2, 1 is a solution. Okay, so I left out a hypothesis here, or one piece of the hypothesis. And so let's say we want to find the general solution to this system, but we're given one solution already, right? Remember, the general solution now is the family of vectors Y such that it's a particular solution plus elements of the null space, X naught, right? This is particular solution. And X naught, this is elements of the null space. Well, in the previous example, we computed all elements of the null space. So really, to find the general solution, we would just need to find a particular solution. But the example gave us one, right? It's too nice of an example. So what this means is the general solution to this system of linear equations is 1, 2, 1, 1 plus, and then those elements of the null space. And so I would say z times 1/3 negative 5/3 1 0 plus w negative 4/3 2/3 0 1, right? This is then, and here this is for z and w, an element of the reals, right? This is for all, in fact, for all z and w in the reals. This is a general solution. It's a family of solutions that solves this system. So I guess if you'd like to see this written as one vector, then this would be 1 plus z over 3 minus 4w over 3, and then 2 minus 5z over 3 plus 2w over 3. And then it looks like we'll have 1 plus z and then 1 plus w, right? Maybe this is a more succinct and kind of aesthetically pleasing answer. Okay, this would be your general solution to the system here. Okay, so this wraps up what I would like to say for, or what I would like to talk about for linear transformations thus far. What we're going to do now is we're going to switch to a really, really important topic of matrix theory. It's called spectral theory. And the basis of spectral theory is computing eigenvalues and eigenvectors of matrices via characteristic equations, and then we'll see some applications. But before we do that, complex numbers are very present in spectral theory and in computing eigenvalues and eigenvectors. So first, what we'll do is take maybe 30 minutes to an hour of a crash course or review session of complex numbers.